Good afternoon, everyone. I'm pleased to be a part of 21st International Conference of Computational and Mathematical Methods in Science and Engineering 2021, and I'm very thankful to the organizers for giving me this opportunity to present my work here virtually in this era of COVID-19 pandemic. And it's good to connect to you, all of you again, and good to see you. Today, I shall be presenting an optimal eighth-order derivative-free family of methods for multiple roots of nonlinear equation, and this is a joint effort of me and my MS scholar together with Professor Alicia Cordero and Professor Juan Ramon Torregrosa of Polytechnic University of Valencia. This is the topical resume of my talk. I shall be giving motivation, a short background, and then of course optimal eighth-order derivative-free family of methods for multiple roots and its special cases that will be treated as new methods, and then the comparison of the new methods is considered in the form of the numerical experiments with the noteworthy previous methods of this domain. Then I shall be presenting the conclusion and future work, and of course the references therein. The problem is to find multiple root alpha with a known multiplicity m greater than or equal to 1 of a nonlinear scalar equation f of t equal to 0. We know that the modified Newton method that was given by Schroeder in 1870 is usually applied to solve this multiple root finding problem. But like we do it for the root finding problem of a scalar equation in the case of simple root, we try to avoid the use of the derivative by replacing the derivative with the divided difference, and we come out with Stephenson method and we present the same order of convergence. In the similar manner, likewise here, we consider the Newton method that was modified by Turab to avoid the use of derivative, and this method also have the quadratic order of convergence, where the derivative is replaced by first order divided difference approximation. During the past years, researchers have developed optimal methods for finding multiple roots of nonlinear equation for known as well as for unknown multiplicity. But most of the method for the known multiplicity, they require derivative evaluation of the known of the involved function. And there are very few which are derivative free, and only one is of optimal eighth order so far. So keeping this in mind, we propose a three-step optimal eighth-order family of method that has the flexibility of choice at the second and third step, and the development also involves the first-order divided difference approximation, or as well as univariate and multivariate weight functions. This is the method that I was talking about. This was given by Sharma and others in 2019, and it is a seventh order method for computing the multiple roots of nonlinear scalar equation. And we see here that it involves a univariate and a bivariate weight function at second and third step respectively. And these are the conditions set under which we see that under the conditions on h and its derivative evaluated at origin, as well as the partial derivative of g evaluated at origin as well, we come out to be with a method which is seventh order convergence. Here gamma is a free parameter. This is the second method that was given by Sharma in 2019, and this is the only method, optimal eighth order method so far, in which we see that again there are some parameters a1 and a2 at the second step, and here hk is defined in the form of uk, and then the third step involves a bivariate weight function again. And under the particle values of a1 and a2 and the conditions on the partial derivative of g, this method is eighth order convergence, and here also gamma is a free parameter. Now we give our optimal new eighth order family of methods for multiple roots, and here also we give a three-step method, and we use a univariate weight function at the second step and a multivariate weight function at the third step, and also uk, vk, and wk, they are given in the form of the function evaluation at tk, zk, and yk. We can do an investigation on the convergence analysis of proposed new family and come out with the condition set of the weight function h and k. And this is described here under the conditions on f and initial gas T naught, which is sufficiently close to the multiple 0 alpha. We see the conditions of h and its derivative evaluated at 0, as well as the conditions on k and its partial derivative evaluated at origin again. We see here there is a free parameter here in the form of partial derivative of k with respect to v evaluated at the origin, other than the parameter gamma, which is involved. Now, from the error equation, it is obvious that this method is 8th order convergence, and as you can see that it involves only 4 function evaluation. So it is optimal in the sense of Kung and Turab conjecture. Now we take the special cases of this family of methods by taking h and k as polynomials, and also we take here k010 as 2. Gamma is free here, and we will take the appropriate value of gamma in the numerical experiments. Let us consider the second special case in which h is taken as a rational function and k is again a polynomial. And again, we take the particular value of k010 as 0 here, and gamma is again a free parameter. For the numerical experiments, we consider the special cases SC1 and SC2, and we compare with the recent derivative-free methods of 7th order and 8th order that were given by Sharma and others in 2019. They are denoted by SH1 and SH2 in the case of 7th order, and SH3 and SH4 in the case of 8th order. We take the value of gamma to be 0.001 for all of these methods, as not only our methods, but as well as the methods that are taken for comparison here. The comparison is done on the basis of the difference between 2 consecutive iterations of the first 3 iteration and the absolute residual error of the test function at the 3rd iteration and the computational order of convergence. And the definition is taken by, that was given by J. We have done our calculation with 100 significant digits to minimize the round of errors, and but we display only the results up to 5 significant digits. These are the special cases SH1 and SH2 from the 7th order scheme of Sharma, and then SH3 and SH4 from the 8th order optimal scheme. For the sake of comparison, we take examples, the nonlinear standard test function, in which the first example, it involves the trigonometric cosine function. It has a multiple 0 alpha at, you can see here 2.034 and so on, and with multiplicity here is 5, we take the initial guess as 2.35. Then in the example 2, we have a polynomial, and it has also a multiple root of multiplicity 6. We take the initial guess to be 1.33. The results of example 1 and example 2 will be displayed in table 1 and 2. In the similar manner, we have example 3, which is a mixture of, you see here, the square root and here the rational form of the underlying unknown variable. And we have also a multiple root here with multiplicity 7. The initial guess is taken as 1.30. The results will be displayed in the form of table 3. Now this is table 1. You can see here that our method SC1 and SC2, they are performing better than the previous method of this domain, the 7th and 8th order method of, and they are not only performing well in the case of the error of the consecutive iterates as well as the functional residue error. Also, the theoretical order of convergence is verified here in the form of computational order of convergence. The same case is in table 2. We see here these are our method SC1 and SC2, and similarly table 3, which is the comparison for the F3 function, having the multiplicity the root having the multiplicity 7. And again, we can see here that SC1, SC2, they are performing in a better manner. So we can conclude that we have presented different iterative scheme in terms of both substeps. Of course, we can present some more special cases, and then the numerical results confirms the theoretical results, especially the theoretical order of convergence is verified by the computational order of convergence. And from the table, it is apparent that from the construction and numerical results that our proposed family is optimal and efficient in terms of small residual errors. For the future work, it is noteworthy that a selection of specific value of parameter gamma as well as the parameter that I mentioned there, K010, it can be made under the point of view of improvement of the stability and unwinding of the set of converging initial estimation. And this will also lead us to choose more stable and widely applicable members of the family. So we are also in doing this stability analysis, as well as we shall also be trying the attraction based fields. These are the references that I have used here. These are the, you can see some optimal 8th order family of methods, but they are derivative based. Then this is also derivative based. And here, these are the two papers of Sharma. They present the 7th and 8th order derivative free methods. These are also the derivative based methods. So thank you so much for your attention and patience. Thank you. If there are any questions, they are welcome. Thank you so much.